Okay, so we're working on problem 13.2. Start this by recognizing that the index of hydrogen deficiency is equal to 1 for this. And as always, we will start by counting the number of hydrogens on carbon atoms. And so we have 0 for a singlet, 2 for a triplet, 1 for a doublet, 2 for our triplets. Okay, note we have symmetry indicated by this number 2, telling us that we have 2 methyl groups. And if we add that all up, we come to the number of 20 hydrogens. So what does this tell us? It tells us that all of our hydrogens are on carbons. Okay, so let's look at the functional groups that we are working with here. Going and looking at our broad overview, we have a peak at 177, which is a singlet. That's coming in the carbonyl region. Okay, we will then go through and remember that we have at 177, this is a singlet. This is too far upfield to be consistent with a ketone. So remember, when we're looking at the chemical shifts of ketones, they would be coming in the range of high 190s to below 210 parts per million. Here we're looking at 177. That's more consistent with with an ester. Okay, so here's some example compounds. Notice that we've got plenty of examples where esters come around 170 to 175. Here we have a chemical shift of 177. So that's much more consistent with the structure of an ester than it would be for a ketone. So we're going to call that functional group out as an ester. All right, so some other points now that we've recognized that we have an ester. We see that we're sort of out of the very rich functional groups. And we're going to notice that we have symmetry in this compound, or remember that we have symmetry. So we saw 119, we have 2 methyl groups. And so we're going to write that fragment down now as well. I want to get a different piece of paper here. All right, so in the C13, we have 2 methyl groups at 19.1. So then we're going to look at the proton NMR and see if we can find those methyl groups. And here we see at 1.26, we have a peak that indicates 6 hydrogens. That's the only one that really seems reasonable for a For a methyl group, there is a multiplet at 1.4, which is 6 hydrogen, but we're going to go and say that this peak at 1.26 makes much more sense. Okay, so with that, we see that that's a doublet with a coupling constant of 6.5 hertz. And so what we can deduce from this is that we have a hydrogen point of connectivity next to that, okay? Okay, so then from this point, let's go back to our ester functionality. We see we have at 64.4, we have a triplet. Okay, and then connected to that at 4.05 in the proton NMR, we have a triplet with a coupling constant of 7.1 hertz worth 2 hydrogens. All right, so from that information, we can go back to our ester and fill in that we have at 4.05. Here we have a triplet with a 7.1 hertz coupling constant, okay? All right, so from that, we can now go and look at what we have remaining. We have kind of, and notice that this isopropyl group, this is an end group, okay? All right, so we've picked that off. We've also, we're remembering that we have taken care of our Sol unsaturation unit. So the ester takes care of our Sol unsaturation unit. All right, so what's left? We have basically to kind of fill in the blanks here. Now we have one more methyl group. I'm going to change colors. All right, so we have this methyl group. It's appearing as a triplet with a coupling constant of 7.3 hertz. Notice that's not coupled. That's a different number than our 7.1 hertz coupling constant here. So then we have kind of a number of multiplets that are left over. Okay, this multiplet here, which is being called a multiplet, is appearing at 2.52 as a multiplet as 1 hydrogen. So remember, we have this isopropyl group, and that kind of is a Sol hydrogen that is really consistent with an assignment, or that we're going to assign as 2.52. Okay, so this is remember, this is real data. We might have hoped that, or may have expected that this could have been assigned as a heptet, but indeed in the data that we have for this problem, the person who assigned this spectrum called it a multiplet. So that's what it's called. That's the reality of what we're going to be dealing with people's interpretations of spectrum when we're working with them. Ideally, this could have been more rigorously assigned as a heptet because of the symmetry of these two methyl groups. Nonetheless, we assign this at 2.52. The fact that it's at 2.52 tells us something. It tells us that it's kind of coming in a position that is next to a group that's electron withdrawing. So this is deshielded relative to where we would expect it to come for an ordinary isopropyl group. So let's look at this table 13.1. So we have a recollection that we have a choice between having, so remember we have methynes, methylenes, and methyl groups. We're going to be looking for the methine in this table. Okay, so that's going to be the double dots. If we have an ester, that methine could be positioned directly attached to the oxygen, at which point it would be expected to come close to 5 ppm. If it were attached to the carbon, then it would come right here at about 2.5 ppm. And of course, that's what we have. So we're going to take from this that our isopropyl group is attached like this, and then we have our ester. And then to complete this picture, basically we have, remembering now that we have a methylene at 65, this would be, again, looking at this, a methylene at 4.05 is completely consistent with that. And then to just complete this out, we just need to fill in the rest of the methylenes. Okay, so I'll just get one more last piece of paper here. Okay, and that should be it. So we will end up with our methyl group here at 0.89. This connects over here to our peak at 14, which is our remaining singlet. Then we have a series of methylenes from 31.6 to 22.6 and those in between. And then we would basically go through, we would assign this 1.64 as a multiplet in the proton NMR, and then we have these 6 hydrogens at 1.4 ppm. Okay, so that's the answer. That's the answer to number 13.2.